Hey everybody, welcome back. This week we're going to be implementing a binary search tree or BST data structure in C++. And our goal is to demonstrate key BST operations and analyze their performance. So let's take a look at a high-level overview. We're going to implement the BST with required functions add, remove, maximum, in-order traverse, and find. We'll also create test cases to verify correct functionality. We'll measure performance for adding different numbers of nodes. And finally, we'll analyze results to understand BST efficiency. Let's take a quick look at the binary search tree.h header file. This header file defines the structure and interface for a binary search tree or BST data structure. It declares a node struct to represent individual nodes in the tree in the binary search tree class that encapsulates the tree's functionality. The binary search tree class provides public methods for common operations such as insertion, removal, and traversal, while also including private helper functions for recursive implementations and tree management. So after our include statements, we have our node structure. And this basically represents a BST node with data and left and right child pointers. And this is followed by the class for the binary search tree, where our public methods and our private helper functions are kept. And then we have our binary search tree.cpp file, and this implementation file provides the concrete implementations for the binary search tree class methods declared in the header file. It defines the functionality for core BST operations such as insertion, removal, searching, and various tree traversals in order, pre-order, and post-order. The file also includes implementations for constructors, destructor, and overload operations, completing the full functionality of the binary search tree data structure. So let's take a look at each of these functions. First, we'll start off with the insert function. The insert function adds a new node to the BST while maintaining the BST property. It uses a recursive helper function, insert recursive, which compares the new value with the current node's value and decides whether to insert in the left or right subtree. If it reaches a null node, it creates a new node with the given value. Next, we have a remove function, and the remove function deletes a node from the BST. It handles it with three cases. First, we have the leaf node, simply delete the node. Then we have a node with one child, and we replace the node with its child. And then node with two children, we find a minimum value in the right subtree or in order or successor and replace the node's value with it, and then delete the successor. And then next we have a find function, which we call exists, and this function checks if a given value exists in the BST. It uses a recursive helper function, find recursive, that traverses the tree, comparing the target value with each node's value to decide which subtree to search next. Then we have in-order traversal. The in-order function performs an in-order traversal of the BST, which visits the left subtree, then the root, and then the right subtree. This produces a sorted list of the BST's values. It uses a recursive helper function, in-order traverse recursive, to build the result string. And then finally, destructor and delete tree. The destructor calls delete tree, which recursively deletes all nodes in the BST to prevent memory leaks. It uses a post-order traversal strategy, deleting left and right children before deleting the current node. And then finally, we have our main CPP file, which implements the binary search tree or BST operations and performance testing. Here's a walkthrough of its key components. So we start off with our header inclusions and namespace declarations. This includes the necessary libraries for input-output, assertions, time measurement, random number generation, and file operation. And this also includes the binary search tree header, which we'd already gone over earlier. And we start off with a file reading function. The read from file function reads data from the specified file and inserts it into the BST. It demonstrates how to populate the BST from external data. Then we have some test functions. Several test functions are implemented to verify the BST operation. So we have test remove from empty BST. This tests removal of an empty tree. We have test insert duplicate node. This checks duplicate node insertion. Test remove node with no children, verifies removal of a leaf node. Test removal node with one child. This tests the removal of a node with one child. And then test remove node with two children ensures correct removal of a node with two children. And finally, test verify BST structure, checks the overall BST structure using in-order traversal. Then we have performance measurement, and this is the measurement add performance function, which measures the time taken to insert a specified number of random nodes into the BST. And then we have the main function, and this creates a BST and reads data from a file that we provided. It runs all the test cases to verify BST functionality. It measures and reports performance for inserting different numbers of nodes, 100,000, 10,000, and 100,000, and then calculates and displays performance ratios between consecutive measurements. So let's run the program and discuss the results. First, our file input and BST structure. The data was successfully loaded from the file, and the in-order traversal, so in our text file that we uploaded into the program, it went from 10 through 100 and shows that the BST was constructed, but it's not perfectly balanced. And this is expected with the BST when inserting elements in a specific order. Next, the functionality test. All the test cases pass successfully, demonstrating that the BST correctly handles various scenarios like removing from an empty tree, inserting duplicates, and removing nodes with different numbers of children. The in-order traversal test, 2 through 8, shows that the BST maintains correct ordering. Next, we have our performance measurements. So as you can see, we have our 100 through 100,000 nodes with the output in seconds. And when we put this into an Excel chart, you can see the time increases as the number of nodes increases, which is expected. The ratio between consecutive measurements decreases. So we have, from about 14 times, 11 times, 8.5 times, indicating that the time complexity is better than linear, but worse than constant. And this aligns with the expected average time complexity for BST operations. So this visualization definitely helps illustrate the BST's performance and characteristics. So that's about it. If you have any questions, please leave a comment below, and I will see you all next time.